In this video, we look at limits at infinity. This basically means we look at functions and we are interested in the behavior as x goes to plus infinity, becomes large positive, or x goes to minus infinity, meaning large negative. A function can do many things. We have seen, functions which kind of converge to zero, or they oscillate, or they grow. And so the question is, what is the behavior as x becomes large? And similarly, maybe what is the behavior as x becomes large negative? Let's start with a definition. So let's assume a function is defined on an interval from a to infinity. Then we say the limit as x goes to infinity f of x is equal to L if the values of f can be made arbitrarily close to L by taking x sufficiently large positive. We can define the opposite for limits for negative numbers. So a function should be defined on minus infinity to a, and we say the limit as x goes to minus infinity of f of x is L if the values of f can be made arbitrarily close to L as x becomes large negative. In other words, we are looking whether the function converges to a finite number L as x becomes very large positive or very large negative. And these numbers do not have to be the same. So it would be maybe better if you write this L1 here and L2 here to firstly indicate that these limits do not have to be the same, and secondly, they do not even have to exist. So here's a wonderful example which you know quite well, which is f of x is 1 divided by x. The function is the standard hyperbola, which looks like this and like this. And we all know as x goes to infinity that the function approximates 0. So I can write limit as x goes to infinity of the function 1 over x. This is in fact 0. I can make it as close to 0 as I want for making x really, really large. Now, if I make x large and negative, I get the limit as x goes to minus infinity of 1 divided by x. Again, the ratio becomes smaller and smaller and approximates 0 from below, which is then here. If this happens, then we call L the horizontal asymptote. So in our example here, 0 is a horizontal asymptote in both directions, in the positive x direction and in the negative x direction. Let's look at a more complicated example. F of x is x squared minus 1 divided by x squared minus 2. Let's plot this first by substituting some values. So if I substitute 0, then I get minus 1, which is here. If I look at zeros as a denominator, I find minus 1 and plus 1 are the zeros, so here and here. And then for the rest, maybe you trust me that the function looks like this. So it looks like this and like this. Now we have many options to graphically represent a function. You all have worked with graphical calculators, you can put it in there. We have worked in class with Wolfram Alpha, you can put it in there. I often use Maple, which is another kind of program, and there are many more. So I claim that the limit as x goes to infinity of x squared minus 1 divided by x squared plus 1 is equal to 1. And I claim also that the limit as x goes to minus infinity x squared minus 1 divided by x squared plus 1 is also equal to 1. Can we prove this? We want to do some mathematics, right? So let's do some math. The idea for a rational function is to take the highest power in the denominator, so I wrote it right here as tip, the largest power of x in the denominator, and then we divide the numerator and denominator by this power. So the largest power here is x squared. So then we do what I just said, and we write limit as x goes to infinity, x squared minus 1 divided by x squared plus 1, and we divide it by x squared, numerator and denominator, x to infinity. This is 1 minus 1 divided by x squared, and in the denominator we have 1 plus 1 divided by x squared. And now I take a red pen and I look at limits which I can already compute. For example, 1 over x squared, this certainly goes to 0 as x goes to infinity. 1 over x squared, this goes to 0 as x goes to infinity. So then together we just keep the ones. So this is 1 divided by 1, which is 1. And this is exactly what I claimed, right? So the horizontal asymptote for x2 plus infinity is 1. And then for limit as x goes to minus infinity of x squared minus 1 divided by x squared plus 1, it's a very similar calculation, and I just leave it to you to do yourself. Here are two more examples. So again, the rule is to divide by the highest power in the denominator, which is here x cubed. So then we can write this is equal to the limit as x goes to infinity. Now it is important that you carry the limit sign as long as you have x in your equations. So what was the rule again? Divide by x cubed. So then we get 1 over x cubed minus 1 over x, right? X squared divided by x cubed is 1 divided by x. In the denominator we get 1 minus 1 divided by x squared plus 1 divided by x cubed. And then again we take our red pen, and then this guy goes to 0 as x goes to infinity. This goes to 0, this goes to 0, and this goes to 0. And so what do we keep? Well, we just keep 0 divided by 1, so then the limit in this case is equal to 0. Let's look at the second example here. Again, limit as x goes to infinity. Now the highest order is again x cubed, so we divide x to the 4 by x cubed. This gives us an x minus 3 divided by x, we divide it by x cubed, plus 1 divided by x squared divided by 1 minus 1 divided by x squared plus 2 divided by x cubed. And then again the red pen, so then this goes to 0, this goes to 0. It's actually fun doing it with different colored pens. And then this is the limit as x goes to infinity of x divided by 1. So I carry the limit sign because I still have an x in my expressions. And this goes to infinity. As x becomes really, really large, the expression x divided by 1 is the same thing, so this goes to infinity. Okay, I think you understood it quite well, but are you up for two more examples? Let's do two more examples. So, for example, sine x is quite special. So how does a sine function look like? Well, we all know how sine looks like. It looks like this. This is an oscillation, and the frequency is 2 pi, so here is pi and here is 2 pi, and then it oscillates between 1 and minus 1, and of course it continues in the negative direction too. So what is the limit as x goes to infinity? So if we go further and further out here, so where do we end up? Do we end up at 1? Or do we end up at minus 1? Or do we end up somewhere in between? It's really hard to say because it continues oscillating. And in fact, we will see later that the limit cannot be computed. So we say it does not exist. So that's the case of a function which does not have a limit as x goes to infinity. And let's look at the last example which I have for you here, which is the limit as x goes to infinity of x squared minus 1/2 to x squared minus 100. What this is, so if you apply one of the limit rules, limit x to infinity of x squared minus limit as x goes to infinity 1/2 to x squared minus 100. Let's just assume we could do this. I tell you later this is wrong, but let's do this for now. Well, the first limit is infinity, and the second limit, as x becomes really, really large, this term will be really, really large, certainly bigger than 100, so this also goes to infinity. So we have a limit of the form infinity minus infinity, and then this is really, really difficult to solve. We don't know what it is. So a better way to look at this problem is to modify first. So maybe I do this here in blue. So this is limit x goes to infinity, and then I just multiply out what I have in the brackets. So see what I get. So it's x squared minus, if I multiply the 1/2 to the 2x squared, then I get x squared. and then minus times minus is plus 50. Then this is limit x goes to infinity of 50. The x squares have cancelled, so this is just 50. So the limit of this expression is 50 and not infinity by minus infinity. So you need to avoid these kind of things because they don't really make sense. And the difference of infinity can be kind of anything, so here it was 50. Let me summarize. If a function f has one of these limits, either limit x goes to infinity f of x, which we call L1, or if x goes to minus infinity, then we call this limit L2. And if one of these numbers, L1 or L2, is finite, or both are finite, then we call y is L1 or y is L2 a horizontal asymptote. And we have seen examples where L1 or L2 do exist or do not exist, or they might be different for x to infinity or x to minus infinity. For rational functions, we found a trick of how to compute these limits in dividing by the largest power of the denominator. Then we get a complicated expression, but we can identify terms which goes to 0 very quickly, and what remains is often, if you are lucky, simple, and then you can compute the limit. Hey Malo, where are you going? You are going to find a limit at infinity? Do you think this is possible? How would you do that? And 3 weeks later,